All right, let's start again. Okay, so like I had said before I started recording, chapter 6, we're going to take 2 weeks to cover. So we have this week, we have spring break week. You guys all know spring break.
Yeah.
You can't imagine nobody. I can't imagine no one knows that. Someone doesn't.
You're actually not even in this training now.
Really?
Yeah, that sucks. Maybe you're like overemphasizing the other side of the board.
Well, that's because I have no choice except for like if I get it more angled.
Yeah, that'd be great.
I mean, the problem is, do you mind moving over one? That might help. Yeah. Sweet. I actually don't even care if you're there. I want your chair. All right, let's try. Let's try it. I should just stop the recording. All right, cool. So what do we say? We were talking about chapter 6. We're going to do it over 2 weeks. Am I still not in it? Nope. Let's do here. Jeez. There you go. There you go. All right, chapters. I'll just use this side. There you go. I'll try. You'll have only one marker board. Next week is spring break. I haven't had a chance to look at exams 2. Exam 2, my plan is to grade it during spring break. Okay. So today is matrices. For next week, or sorry, for 2 weeks from now. What is that? April 3rd, 4th? Does anybody know? April 2nd. Thursday's April 2nd?
Oh, no. Sunday's March 31st.
I think it's April
4th. Monday's the 1st, so April 4th.
Yeah. For April 4th, I want to make sure if you haven't had a chance, please read chapter 6 or whatever chapter it is in your book on matrices. Okay. I have posted a book on linear algebra, the entire PDF. It's a scan. It's not a digitized version, really. It's a scan of the PDF. It's a scan of the book. It's by Gilbert Strang. He is an excellent teacher of linear algebra. He teaches it from the engineering and applications perspective. I do not expect you to read the whole book. But what I would like you guys to read is chapters 1.1 through 1.5. Okay? They are pretty intense. They're pretty intense chapters, I'll give you that. But he gives you this soft introduction to linear algebra, which is really what we're going to get into with matrices. Not today, but in next class. And sort of give a little bit of the motivation about how it all works and how it all fits together. So I hope it gives that context that's super valuable for you, whether you're taking a linear algebra class or not. Yeah, it's a little soft introduction. Yeah.
Is the fact of the writing in the video?
There's a way to fix that. I don't remember how to do it.
Yeah, probably.
Has it been that way the whole time?
Once for the past several months.
Just for everyone you've done so far.
Is that better?
Yeah.
I hope that actually records that way. We'll see. Because it's being...
Boy, it's smooth as butter.
I know. You guys are too sharp. All right. The point is, read the Strang book.
Which is already posted?
It should be already posted. Cool. It's in the under assignments. It says read Strang, and if you go click on that, it's a file attachment, a PDF file attachment. Okay. I do not expect you to walk away with this amazing like mastery of matrices and matrix multiplication after reading that section. Okay. It's really just give you some context, give you a soft introduction to like why matrix manipulation is the way it is, right? Because what will happen is, if we don't do that, and I show you matrix multiply, you'll be like, okay, what guy on what drug came up with that?
Yeah, exactly.
Right? And so I'm hoping that this just gives you a little context, you know, perhaps even to whatever engineering discipline you're headed to, you might start to see a little bit of that. And actually, if you get into the rest of the book, you will see it. The one I posted is the 3rd edition, and it's funny because there's a bit of a humor that I have in some earlier editions that's not in this one, which I thought was like, why do you get rid of it? It's very dorky. Yeah, I can show you my editions. I don't remember these.
Okay.
But it's lacking in this one. Okay.
Because he lost his sense of humor after studying this.
I think what happened is people, like, students or faculty complained or something.
They like didn't hate you or something?
Maybe. Yeah, you know, sometimes this stuff happens. In addition to that, there's a homework 8, which is not fully built out on Canvas yet. The basic shell of the idea is there. You can take a look at it, but I'm going to keep building it out this evening and tomorrow. And it'll be ready. We'll talk about it when we go to the labs. Okay? We ready to do this?
Yeah.
All right, good. Let's do it. Matrices, matrices. We have seen a little bit of these already. And what we're going to do now, actually, I'm going to turn off this because I think that's just distracting. Is that fair? There we go. And I still have some of those lines, right? I think so, yeah. Okay, so I can use all that. You might not see me, but at least you hear and see the writing. So before we get really too far into matrices, I want to sort of make this note that there are two very different ways of looking at matrices in the world of programming in general, but also in MATLAB, okay? And when we think about these matrices, we can think about the one sort of way of using matrices that is really just to represent tabular data. Tabular data is a fancy way of saying a grid of data. An Excel sheet is tabular data. It's something you're familiar with, but you've never probably seen that term. Tabular data. A grid of data is another way to think about it. Excel, e.g. Excel, grid. You have rows, you have columns, you have a bunch of data. The second treatment of this term matrix becomes a special treatment. And in that world, we go to very unique definitions of matrix manipulation of those objects, where matrix operations are clearly defined and are not your intuitive, conventional way of looking at them. So special mathematical objects with defined matrix operations. Oh, could you try to choose a different chair, please? Thank you. That one's very precarious. That's all. I didn't want you to get hurt. It won't be as loud as that door slamming, though. Jeez, that scared the Jesus out of it. So everybody, conceptually, does this sound? Is this sound? Or do we have questions about this? Okay. Today, we're going to focus on this stuff. I do not think we're going to get to this today, and this will be next class. Okay? Good with that? All right, so let's start with a concrete example of tabular data, okay? We'll use the one the book gives. Han gives this example, right? He's like, assume you have a bunch of factories. We'll call them factory 1, factory 2, and factory 3. And you have a bunch of stores. Call them store 1, store 2, and store 3. And you want to capture a relationship between each of them and say, what is the cost of delivery between factory and store? And so you could go from any one of these factories to any one of these stores, and you could represent that as tabular data or a matrix. So let's just come up with some numbers. Let's say from factory 1 to store 1, it costs $10 to ship an item. From factory 1 to store 2, it costs $14. I'm just going to put some random numbers in here. The numbers are not really important. We can store this in what's called a matrix. And since I'm dealing with cost, I'm just going to make this matrix C. And typically, we don't draw a box and all that stuff. We just draw big square brackets. So in the real world of math, I might just represent this without this box. And without these, but rather just big square brackets like so. Now, there's nothing about this that tells you I am in the land of tabular data or I am in the land of mathematical objects that I'm going to do matrix operations with. MATLAB doesn't differentiate between those two. You've got a matrix, call it C. Whether you're here or here is how you use that data, how you use that matrix, how you manipulate that matrix. It's up to you as the programmer to decide which realm you're in. You can go back and forth between them, possibly. Better. Cool with that so far?
Yeah.
Okay, good. So then you might have, you might present yourself, you might write a piece of code whose goal is to figure out like, okay, well, if I have this relationship between my factories and my stores, how do I reduce my costs? Like, what's the cheapest way of running this business? Should I maximize production at factory 1, 2, or 3? Should I maximize distribution at which store? Which store has the most number of customers, sales, et cetera? It could become a really interesting optimization problem. And eventually you might have what you might call a solution matrix. So just pretending we know how to get the math from here to here to get to a solution for our problem. The solution being, what's the best way for me to run my business, right? Like, where should I be shipping the most items? And so I might end up with something like, well, I should do the most 3 here, sorry, might do 5 here, but I don't think anything should happen between these guys. Let's do 1, 9, and 7. Maybe this is the most optimal result. That would be my solution. Everybody still with me?
Yeah.
Cool. So if I were to ask a question like, okay, well, interesting. I have a solution matrix. I have my cost matrix. And the question is, well, how much is it? What is the total cost of me running this thing? Given the solution as it is, given the cost matrix as it is, what is the, how do I determine the total cost of running this operation? Just to be clear here, this is cost per whatever, let's call it widget, the classic, right? Cost per widget to go from the factories, which are in rows, to the stores, which are in columns. And that relationship is down here too.
What is the numbers in the solution matrix represent again?
Good question. This is cost. Okay. Let's say our solution matrix is expressing the number of widgets between any given relationship, between any given pair. The top is the cost per widget between any given. And the thing I'm looking for is total cost of operation. What do you guys think? We've seen this already, which is why, we've kind of seen it. Don't tell me about MATLAB. Just tell me about, conceptually, what do you think we should do? What math should we be trying to do?
Well, we want to know the cost, the total cost by multiplying the individual number of widgets by the cost per widget.
Okay, so we could peel back on this problem, right? Because total cost, that's a big problem, right? We could peel back sort of in our algorithmic approach and say, okay, well, what would it take to figure out the cost just between one relationship? So between factory 1 and store 1. Let's just start small. How do I figure out the total cost of that operation? Yeah, exactly. It becomes this times this. Okay?
Yeah.
$10 per widget. I'm going to do 3 widgets between factory 1, store 1, multiply them. It's easy, right? So, all right, well, let's actually build out our total cost of operations matrix, okay? In the row 1, column 1, what value should I put? Multiply 10 by 3, I get 30, right? So then, okay, that's fair. How about between factory 1 and store 2? Yeah, so I shift over 1 in both.
7.
7? Yeah. Cool. And I keep going, right? So what type of multiply is this? We've seen this already. What type of multiply is this? We've given it many names. Yeah, we've called it a scalar multiplier. Anybody else remember a different term we've given it? A dot multiplier. Let's not say dot product, because that actually has a difference. And the only reason we call it dot multiply is because the syntax is dot star, right? You guys remember that, right?
Yep.
You said that If you're dealing with matrices and we're doing some multiplication, the whole first half semester we said use the dot. Because if you don't, you transition into that special matrix math, the special matrix multiplication that has its own other definition. Okay? So you dot multiply, what else have we called it? Remember element by element? Remember that one? Element by element is sort of the most descriptive, right? It says I'm going element by element, right? The other ones are a little bit higher level ones. There's also another term, it's called array multiply, I think. Array product. So these are all effectively synonymous and telling you that you're going to take each element, its corresponding row column location, and multiply it by the other. Yeah. What happens if my dimensions don't match between these two things? Yeah, MATLAB gets upset, right? Cool. Okay. So take me through the next step, right? I've described how I can just get the sum of each of these. From an algorithmic perspective, then, how do I get the total cost of my operations? Yeah, so I have to add up. If I add up all the elements here, then I'll get the total value. Does everybody see that? Yeah. Yeah? Okay, cool. So let's pause there, switch to MATLAB, and try it. Try not to get my head chopped out. Does anybody remember what drive that is? All right, can you guys see that? No. Why is that? Why are you guys not yelling at me? You guys are just shooting the shit over there. What are you guys talking about? Spring break already? When spring break start? Tonight? It starts. Tonight is not going to go well. You know, I told you guys at the beginning of the semester, if an invitation was given, no invite. I can tell you, I know where I fall on the pecking order. Yeah, blame me now, huh? I haven't got a single offer, I tell you. All right, so let's do some fun basic matrix. Yeah? You guys all remember how to do this, right? You haven't forgotten it all.
Yeah.
All right, cool. So let's make a cost matrix. Now, I'm just going to go back to the command window. You guys remember how we build a vector, right? With square brackets. Same exact way we build a matrix. With the is it too small? Yeah, sure, totally. Thanks for asking. Somebody made it smaller, huh? Probably me from last time. 24, is that too big? That's going to be too big, I think. Sure. Let's do 20. Is that good? Yeah. All right, cool. All right, so let's see here. So I can do a little matrix like this. Got square brackets, 10, 14, 11. Does anybody remember how I get to the next row? Semicolon, right? I can also do, there's another trick I can do. You can go carriage return. So it's your choice. You can do return to get to a new column, a new row, or you can do semicolon. Yeah, so here we didn't, I skipped the semicolon business. Totally your choice. You can do it either way. Do it either way. All right. If I was making a really big matrix and I didn't know how big it was, how could I tell how big it was? You could do whos. Whos is a super easy way to do it. So we do whos. I see that matrix C is there, and I see that the dimensions are 3 by 3, right? Remember, in matrix land, MATLAB land, the first number is always the row. Second number is always a column. Okay, we're going to see that even more today. Cool. All right, so I can just copy and paste this into my script. Let's see here. Oops. There we go. I am going to put semicolons here. There we go. Okay, that should work. And we got a solution matrix, right? What do we call it? X. One of my values here, 3, 5, 0. And if I use semicolon, I can actually keep it all on the same line. So here you're seeing a little variety of ways you can do this. Whoops. Bam. All right. And now I want to do an element by element multiply or an array multiply. How do I do it? Yeah. All right. So cost matrix equals C dot. Actually, I'm going to take these out just so we can see how it does it. Okay. Here we go. I'm going to save it. I'm going to go over here and say run it. And it doesn't like something. What did I do?
Yes, basically dot start.
Oh yeah, that's bad news there. There we go. All right, so we see that we have our cost matrix, we have our solution matrix, which we're not getting into how we came up with that today. That might be something we do more advanced later. But assume we have some fancy algorithm that comes up with that tells us, hey, this is how you should do your factory production and shipping. And multiply element by element, we get our cost matrix. Okay. Now, the ultimate goal here was we wanted to sum it all up, right? Does anybody remember a function that helps do that for us? Sum. Okay, and we're going to learn something cool here. I'm going to try sum on here. And all these variables are here, so let's just do it in the, I'm just going to do it in the command window. I'm going to say sum of the cost matrix. You may intuitively think that it's going to add everything up for us, right? And it's not going to do that. So if you've played with these built-in functions in MATLAB a little bit, you will have noticed that there are some behaviors that are interesting. I'm jumping ahead a little bit in my stuff, but that's okay. Yeah. Okay. So what do we think happened? So looking at the data above and looking at the data here, what do we think happened? Sort of empirically. If by columns, right? So depending on the function, this is function specific. MATLAB, when given a matrix on that function, one of the things that it might do is apply that function element by element. Okay, that is one possibility. And the other possibility is it's going to do the function column by column. Now, what you actually get depends on which function it is. If you really want to know definitively, you've got to go help that function and find out, right? So option A is the function acts element by element. And option B, the function acts on columns. Okay? If you were just to kind of think through this sort of like algorithmically maybe and sort of come up with an intuitive answer, can you give me a guess as to the type of MATLAB built-in function that would operate element by element? Shot in the dark.
Multiply.
Forget it. That's more of an operation rather than a built-in function. Let's think about built-in function.
You say sum cost matrix colon in, so like beginning to end.
Oh, I see. Let me ask the question differently. Think of another built-in MATLAB function whose default operation is A as opposed to B. So B's default operation is sum.
Round.
Why round?
Well, it would be just rounding. It would be changing what I don't. It would be truncating individual numbers.
Yeah, like does it make sense to round a column together? Like,
yeah.
There's no aggregation of numbers, if you will, right? Sum clearly is designed to take many numbers and get you to one number or some smaller set of numbers, right? But round is not designed to do that, right? So like if you kind of think through that operation, like how would round do a whole column together? It just doesn't, it doesn't jive, right? So another example are trigonometric functions. If you do sine on a matrix, it's going to do element by element. It's not going to go and do the whole column. So round is another perfect example. Sum is an aggregation function. What are some other aggregation functions? Max.
What do you mean by aggregation function?
Takes a bunch of numbers It gives you one number back.
Min.
Min,
Average, mean,
average,
Median.
median. Okay, let's try them out, shall we? So, Max, who gave me this chair? Is this some sort of practical joke?
No, they're all doing that now.
Right? So, here's cost. Yeah, sure. I'm supposed to believe you that, right? Like believe that, right? This is exactly what we're getting here. The max pulled out column by column with the max value, right? So you guys are on the right track, right? So functions where it makes sense to do a combination of combining numbers, basically an aggregation of numbers in some function that's defined, is going to do column by column. So then the question is, okay, let's do column by column. How do I do the sum of the whole thing? Yeah. Yeah. So you basically, if you want to do a sum of a whole matrix like that into a single value, you effectively nest your functions. Okay? Just like nesting for loops, just like nesting conditionals, etc. You can nest functions. So sum cost matrix gives you that. Okay? And internally, what is happening is we start from the inside and we work out. The inside function says take cost matrix, which is a 3 by 3, and do sum. Sum's going to go by columns. Okay? You then end up with a single vector of results, which we've seen here, right? Somewhere up there we saw one. 3 values in a vector. If you do sum on a vector, it collapses all of the values in that vector. You get a single value out of it. That's the operation of the outside sum, and you get 17. Would this method work with max? I want just the single largest value of the whole matrix. Yeah. Would I use sum and max together, or max and max? Max and max. Yeah? Now, sum and max together does something different, right?
Sums up the maxes of each column.
Yeah. Or it gives the max of the sums. It depends on the order, right? So they're going to give you very different responses. Or not very, but different responses, right? So let's try both, right? So I'm going to go clear, C. What's it called? Basic. All right, so there's my cost matrix, right? Let's try this one first. Max, sum, cost matrix. Now, before I do this, what do you guys think will be the result?
One
Max
output.
of the sum.
It will be one value, but what will the value be?
It's gonna be that max of the sum.
511.
Give me a number.
511.
511? All right, good. And if I do it the other way around, what am I going to get?
627.
What does everyone think?
Yeah.
Oh,
649.
649.
That's the idea.
It was in the right ballpark.
If instead of like rows, you wanted to do the sum of the column, or like,
Now this is columns.
yeah, if you wanted to do the sum of the rows instead of columns,
Yeah.
could you put like an apostrophe?
Yes, exactly. So we've seen this before, the transpose. If your data is tabular and you're really just trying to analyze it in, the default behavior is to do columns and you need to do a row analysis, you could transpose the matrix first, dump it into your built-in function, and you'll get the result. Let's try it. Yeah. What happens if we do, let's just do the native one first, if you will. This is the columns of cost matrix, right? And if I put this in here, oops. Okay, what do we expect to get as a result now, right? The first time we did sum, we got 38, 178, 511. What do we expect to get as our results?
90 and 649. 100, 0, something over 600. Oh yeah, 100.
Yeah. Now, here's the question. Is it going to be presented as rows as you were hoping, or as columns? It's going to come back as columns, right? Because that's the default behavior of sum.
What if you did it outside?
I was going to ask you about that. So what can we do? We can do that.
Okay.
So you initially are transposing it to give sum the data in the way that you need to give it to get the result you want, and then you're transposing again to get the data in the format you actually want.
But if you only put one on the outside, it would find the sum of the columns and then just.
And then it would flip it. Yeah, so we would get the same result as earlier, Now, I actually think there is a built-in function called sumRows, but not worried about that. That wasn't the point of this discussion, right? The point of this discussion was to see that you can do these things. That's not going to be the case for every function that's out there. Cool. All right, how do we feel about that so far?
You good?
Yeah? All right. So let's take a break from MATLAB for a moment. So now that we've got this fancy matrix, we will want to be able to sort of probe or investigate our matrices, and we'll want to do them in sophisticated ways. We have seen indexing for vectors, right? What's the syntax look like for that? If I have a vector called B, and I want to get the third value out, how do I do that? What kind of parentheses?
Curvy.
Like that?
No.
Not that curvy.
Not that curvy? What manner of curvy do you speak of?
Bent curve.
It's like a third of a circle.
That kind?
Yeah.
Okay. And what do you put here?
Row and column.
The position number, right? So because we have a vector here, so there's only a single number, right? So let's say I want this third one. I should have used 1, 2, 3, 4. That's a bad idea.
Yeah.
And if I want the third value, I index it this way. Remember, MATLAB starts indexing at 1, which is not always the same as other programming. That's a result of, you will see from matrix, from the strang explanation too, you'll see why that's. Cool. So if we then move to this guy, let's call this guy T. And let's say it's populated with a bunch of values. Like so. And I want to pick out some value from it at a given location. I can do that with subscripts or indexing as well. And you might, let's say we're trying to get this guy, okay? You might guess what the way to do that is. It's also with parentheses, but now we give it 2 values. And can you guess what the order of those values are? Row column, right? And so, how would I index this location where the 70 is?
1,2.
1, 2. Yeah. We okay with that? Okay.
So a space wouldn't work then?
That's correct.
Okay.
Because, well, okay, there would be a way to do a space. So I want to do that right now.
Come back to that.
Yeah, we can do that right now. Before I get to that, let's talk about, yeah, so let's continue with this example, right? So even if you have a matrix, there is a way to specify only a single index as opposed to these subscripts or 2 indexes. And if you do that, if T is a matrix and you give it a single value, put it away. If T is a matrix and you give it a single value, this thing gets unwound. And what that means is it treats it like a vector where the number after this is this guy. So it's like putting this up here, putting this after that, and then find the 7th position. So another way to do that is 1, 2, 3, 4, 5, 6.
I don't think that's
7.
right. I think it goes down, then right, then down, down. Because we,
In the book.
Does it go down now?
Sounds different.
yeah, we were trying to figure it out earlier.
Are you sure?
It's what it said in the book.
Okay.
I couldn't figure it out, and Jaime decoded it.
Let's just try it.
Because left and right is how it counts the panes.
You guys are awesome. Let's try it. I said you guys are awesome. Oh, all of you guys.
But you'll be paid more than others.
I didn't say that.
Definitely not that.
I did not say that.
Yeah, I said.
I just
No. Where's the stop share? Oh. There we go. Okay, there we go. All right, there's our cost matrix. Let's try 7. Let's just do 7.
8 or 0.
Oh, there you go. You guys are right. So it's
That's ambiguous.
no, it's not. It's. I mean, there are other zeros, but I think you guys are right. So it's going down. Sorry. So the unwind happens. The unwind happens in the other direction. Lovely. There you go. Okay, cool.
Non-intuitive. Thanks. Thanks, Matt.
Thanks, Matt. Yeah.
So T7, 15 in this instance.
Yeah. So what does T of 7 in this example come out to be?
15.
15. Yeah. Oh, good. I didn't write it yet. What did I do with my other? Thanks. Anybody notices my blue one? Let me know. All right, cool. So you can unwind your matrix like so. Okay.
It's behind your bag.
Thanks. Hiding. Sweet. All right. Transpose is on my list of things to talk about, but I feel like everyone's got that. The apostrophe will give you transpose. Okay, cool. So let's do the colon operator, and then I think we'll take a break. So we've seen the colon operator already. How have we seen it? You guys remember?
Vectors go by increments of 1.
In creating a vector, right? Exactly. So I can easily create a vector like this, and this gives me the range from 1 to 100. Because I have not specified an increment, it's going to go by ones, right? Great. And if I wanted to specify an increment of 5, what would that look like? Excellent. Okay. So this same property of the colon is leverageable in subscripting or indexing. And what we can do here in this example is say T. And let's say I want both of these values, both of the columns in row 1. So I specify row 1, and then I could specify 1. Actually, let's do it slightly differently. Let's say I want all of these. Okay? I want 1, 2, and 3. One way of specifying those locations is to actually put a little vector inside of your indexing. And those locations are described like so. Okay? And what this says is vector T, row 1, all the columns specified by this vector, 1, 2, 3. We okay with that? Okay. Another way to do exactly the same thing is 1, comma, 1, colon, 3. What happens here is the same exact colon operation that's occurring here. The 1, colon, 3 gets expanded to basically look exactly like this. 1, 2, 3. Are we okay with that? All right. And then finally, in this special case, because I only have 3 columns, I can use a special use of MATLAB's colon, which is colon by itself, which means the entire, basically all elements that match that. So this is row 1, entire column.
Row 1 entire column, or row 1 entire row.
Sorry, all columns. Thank you.
So would you be able to do entire column by
Yeah, you
putting
can-
a semicolon on this?
Yeah, exactly. You flip it.
So those are rows, right? Those are rows. So we would be getting 30 through 15 and 12, right?
In all of these cases, you're getting row 1 and every column of row 1.
Okay.
So here you're saying explicitly, you're saying row 1, columns 1, 2, and 3. Here you're saying row 1, columns 1 through 3. So that's the same. Sorry, row 1, columns 1 through 3. So same result. And then here you're saying row 1, all columns. In all 3 of these cases, in this example, you get the same results. Okay? We could change this. Let's change this just a little bit so we can be super clear about a slightly different result. So if I change vector t to look like this, would we say that all three of these expressions give us the same result or not?
No.
No. Which one's different?
The last
The last one, right? Yeah. This one's going to give us 4 values. These two are going to give us 3 values. Cool. So you can also get kind of clever here. Let's say t is our modified version. You can actually do stuff like this. Which says row 1, columns 1, 3, and 4. So you can skip columns. You can skip whatever pattern you want. You can say 1 and 35. You can pick out whatever columns you want. One last little, so this is a special treatment of colon. Special treatment of colon. The other special function, special keyword here when dealing with subscripts is end. Anybody want to take a guess as what that gives you?
1.3.
The last value, yeah. So this is row 1, last column. What would it look like if I wanted column 1, last value?
And 1.
1, yeah. Column 1, last, sorry. Yeah.
Oh, right, yeah.
Column 1, last row. Yeah. Okay, and let's see that real quick, and then we'll take our break. All right. So we got cost matrix, right? And let's do cost matrix 1, comma 1, 3. Let's try that one first, right? Whoops. Does that look right?
Yeah.
Yeah. What do you guys think?
Mm-hmm.
Okay. All right, good. I can do 1, 2, 3. That gives me my whole first row, right? I can go like so. Do the same thing. Right? I can do this. 0. Looks pretty cool, right?
Could you do brackets on the first, like the rows, like 1, 2, 3, 1, 2, 3?
Oh, yeah.
Do the diagonal.
Yeah, you can. Except it won't be given to you as a diagonal.
Hmm.
1, 2. Should work. Oh. Okay, that was not the result I was expecting, but there you go.
So what's happening right there?
It was giving you everything.
Yeah.
You'd almost want to ask for them individually.
Well, I think that's what MATLAB's forcing you to do, yeah.
Like do a loop.
Let me think about this. If you do that. This is because it's trying to support this concept of submatrices. So this might be, the reason it's doing this is because it's trying to support submatrices. And what I mean by that is, okay, let's do T equals, so here we go. I got my random matrix, so let's do this. So here, I got a 6x6 matrix, right, of random numbers, and I can actually pick out a part of it and build that as a sub matrix, if you will. And what I mean by that is I can say like, hey, give me this part right here only, and we can do that by saying basically, what is that? 1, 2, 3, 4, 4, 6, 4, 4, 6. And since it supports that behavior here with 4:6, I think if you give it a vector where you're specifying the rows and columns like that, the default is to treat it more as a submatrix rather than picking out the line. Because you could easily say, well, this could give you that diagonal here, but it's built to give you the submatrix, right? Now the cool thing is you can use this indexing in reverse, the subscripting in reverse. And that is, here we use it to say, give me those values. But you can also use it to say, modify only those values. And that just looks a little bit different, right? So here's T again, and I say this, and if I'm right, sometimes MATLAB doesn't work with me. If I'm right, this should put a 1 into all these values. So you can use this indexing both on the side where you're saying, tell me about the matrix, but you can also use the same exact indexing pattern to say, change the matrix, but only part of it. So you can use the same indexing to say, change only a column, or change only a row, or change only one value. Right? So let's try that. Let's say if I wanted to change this location right here, this 3 here, if I wanted to change that to 4,000, how would I do that?
3.4 or 3.3, excuse me.
Equals 4,000.
Oops, I made it 400. Yeah. So you can change one value, you can change multiple values, but clearly if we specify multiple rows and columns, you're now in a submatrix reference. Yeah, there may be a more clever way to do it, but I don't know off the top of my head.
So what does the end on the 1 do?
Oh yeah, awesome. Let's try with T. What do you guys think T end comma 1 will give us?
Bottommost row and the first column value.
So bottommost row, the last row, end gives you the end in the row position says the last row, and here we're specifying the first column. So in this case, the number will be 4. Yeah. And in this case, what number will we get?
25.
Yeah. And if I flip it around, what should I expect to get?
31.
And if I do
And
this, what should I expect?
65.
How do we feel about that? Cool. All right, let's take a break because I want to do what I want to do. You guys can start thinking about this a little bit. And if you think you have the answer, don't say anything. But I want to take matrix data and I want to do nested for looping through it. So I can do kind of what you propose, which is look at things element by element. And this is because I want to get to a place where we can do an element by element analysis of data that isn't really an intuitive matrix operation. There's some more sophisticated engineering analysis that we want to do element by element. Let's take a break and we'll come back and talk about it. So let's see, what time? Let's come back 1/4 after. So if you need to get coffee or something, go get coffee. Let's chop it, and I'm going to stop the video.